ஆமா.
Welcome, Professor Raul Polcon. We will start within another 5 minutes. Niveda, shall we start? Niveda, please start the session.
Welcome back all, and now we move on to the next technical session of the day. For this, I call upon Dr. L. Vidyarani Ma'am, Assistant Professor, PG and Research Department of Mathematics, Kogunadu Arts and Science College, to welcome and introduce the speaker of the session. Ma'am, please.
A very good afternoon to one and all. It gives me great pleasure to introduce our Honorable Speaker, Dr. Ron M. Falcon. He is currently working as Associate Professor in Universidad de Sevilla, US. His interested research areas are combinatorics, Latin squares, Hadamard matrices, non-associative algebras, algebraic geometry. He has published around 30 papers in reputed international journals since 2016. Gaining knowledge is the first step to wisdom. Sharing it is the first step to humanity. Now I invite Dr. Ron M. Falcon to share his knowledge on the topic, New Advances Concerning Critical Sets Based on Latin Square Autotopism. So please. Sir? Sir Falcon, sir? Falcon, sir, you're muted. Falcon, sir, over to you.
So please, your voice is not audible to us, sir. You're visible to me, and your screen was visible, and we are not hearing you. I'm seeing you. You have unmuted your audio, but we are not hearing you.
Do you listen to me now?
Yeah, perfect, sir. Now it's fine.
Okay, I don't know what is the problem.
So now fine, sir. I can hear you.
Okay, do you listen to me?
Yeah, it's fine now. No issues.
Okay.
Thank you with the presentation, sir. Nice to have you.
Do you see my screen?
No. So probably you can stop presenting and you can reshare now. I hope.
Okay, let me see it.
Yeah, now it's visible, Professor. You can.
Okay.
You can go ahead.
Thank you.
Thank you.
Thank you so much. Okay, thank you so much. Well, sorry for the inconvenience. I had a problem with the sound. Well, first of all, thank you very much to the organizers for the presentation. and well, for giving me the possibility of talking about this topic, in which I am working with Laura Johnson and Stephanie Perkins. They are professors of the University of St. Andrews and the University of South Wales in United Kingdom. Do you see my mouse? Because sometimes it's important. Do you see my mouse in the screen? Well, okay. I think that you see it. Well, let's start. Okay, the contents of this talk are the following. I am going to speak about some advances in critical set based on Latinx squares autotopias. So I am going to show you some preliminary concepts to understand the talk. After that, I am going to speak about critical set based on Latinx squares autotopias. And finally, I am going to show you some open questions about this topic. So let's start. Well, first of all, I have to show you which is the concept of quasi-group. I am going to introduce this concept. It was introduced by Ruth Moffat in 1935. A quasi-group is a pair formed by a finite set and a product that both function AX equal B and YA equal B have unique solutions for all X belonging to the set and for all AB belonging to the set. Okay? Well, sorry, have unique solution for X, Y belonging to the set. Okay, is everything okay? Do you see the screen? Everything is okay?
Yes, sir, it's fine.
Okay, thank you. Well, the important thing is that the multiplication table of a quasi-group is a Latinx square. A Latinx square is an array, a square array, in which have n symbols, and all the symbols appear exactly once per row and exactly once per column. For example, you have here a Latinx square of 4, therefore you have the 4 symbols, 1, 4, and you can see that there are no repetitions per row and there are no repetitions per columns. In fact, I have colored each symbol in a different way, so you can see that you have these two possibilities, or numbers or colors. The interesting thing is that, well, here you have the multiplication table of a quasi-group, but when a quasi-group is associative, then you have the concept of group. So a Latinx square is a generalization as multiplication table of the concept of group. Well, Latinx squares were not introduced by Moffat. Moffat introduced the concept of quasi-group, but Latinx squares is the concept is previous. So everybody knows perhaps the concept of Cayley table, is the multiplication table of an algebraic structure here, or the original works of Leonhard Euler of Latinx square, for example, the problem of the 36 officers. But they are not neither the origin works on Latinx square. So here you have of Latinx squares of in the 1700, or Ramon a lot of time before. In this case, you can see that this Latinx square is a Latinx square of order 4, and if you see the symbols, they correspond to the symbols of water, earth, fire, and so on, that you can see that the meaning of this Latinx square is something magic, no? Because Latinx squares at the beginning was like something with magic, related with magic. In fact, if we go back, we can see some other Latinx squares in the Arabic world, and for example, these are one of the first Latinx squares that are known, that were found in some earrings in Damascus. Okay, so it doesn't matter which are the symbols of the Latinx squares. So you can see with characters, with colors, with numbers, it doesn't matter. The important thing is that there are no repetition of symbols per row and there are no repetition of symbols per column. This is a Latinx squares, and now let me introduce the concept of partial Latinx square. A partial Latinx square, you can think on it as a Latinx square with empty holes. So in this case, you can see that you have a partial Latinx square of order 4, in which the symbols are or the numbers or the columns, you can see that there are no repetition per rows and no repetition per columns, but you have empty holes, empty cells. There are a representation of partial Latin square that you can see here, which is the entry set of a partial Latin square. The entry set is a set of triples in which each triple is forming the row, the column, and the symbol of the partial Latin square. So in this example, you have a partial Latin square of 1, 2, 3, 4, 5, 6, 7, 8, 9 entries, and each entry is related with the entry set in this way. For example, the first one that you have here in blue is the first row, first column, and first symbol. So you have the entry 1, 1, 1. Second one is first row, second column, and second symbol. So you have first row, second column, and second symbol. You have 1, 2, 2. The third one is 1, 3, 3, and one, for example, I don't know, for example, the last one. The last one is the fourth row, the fourth column, the third symbol, and instead you have here this element, the element 3 in the left corner of the partial Latin square. So we have a way to represent a partial Latin square by means of the entry set. Okay, so a critical set. What is a critical set? A partial Latin square is said to be uniquely completable to a Latin square if you can complete the empty holes by means of numbers or symbols in such a way that you obtain a Latin square. So, for example, here you have a partial Latin square, it's the same of before, and you can complete, for example, in this cell, in this middle cell that you have here, you can complete with a 4. Okay, you have 1, 2, 3. So here in this position, you have to include a 4. So you include this 4. And you can complete all the other empty holes in a similar way by means of this procedure of no repetition of symbols per row and per column. It's like a Sudoku. Perhaps you know the game of Sudoku, so it's like a Sudoku. It's not a Sudoku, but in fact, a Sudoku is a partial Latin square that you have to complete to a Latin square. So a critical set is a partial Latin square which is uniquely completable such that any proper subset of entries is not uniquely completable. So, for example, the previous one, the previous partial Latin square, is not a critical set. Why? Because I can eliminate or remove some of the empties, some of the symbols in such a way that the new partial Latin square is also uniquely completable to the Latin square, to a unique Latin square. So, in this case, you have an example, which is this one, in which you have a partial Latin square of 5 symbols, these 5 symbols that you have here in the left, and you can complete in a sequential order. You have the sequence of completion, and finally, you obtain a Latin square. So this partial Latin square is uniquely completable. And in fact, it's a critical set, because if you remove one of the 5 symbols, then you can complete it in at least 2 different ways. Okay, so if you can complete it in 2 different ways, it's not uniquely completable, and so it is not a critical set because it's the smallest number of symbols that you require to obtain uniquely partial Latin square. So this is the concept of critical set. Let me introduce now the last concept of this talk, which is the Latin square isotopes. Which is an isotope? So let's work on the symmetric group, on the set of symbols n equal 1n. Okay, you have the symbols. We are going to forget the colors. We are going to work in numbers 1 to n, and Sn is the symmetric group. So the triple Sn, Sn, Sn in Cartesian product is called the isotopes group of a Latin isotopes group. In such a way that if I have a alpha, beta, gamma, okay, if I have a triple alpha, beta, gamma in this group and a Latin square, I can use this alpha, beta, gamma to act the Latin square in such a way that the entry set of the new Latin square that I am going to obtain is obtained by applying alpha to the rows, beta to the columns, and gamma to the symbols, in such a way that the new entry set is alpha I, beta j, and gamma k. Example, You have here a partial Latin square of order 4. In fact, the last row is empty. It can be, okay, it is not a problem. In fact, you can have all the cells are empty, and this is not a problem. It's the empty partial Latin square. But here you have a partial Latin square of order 4. The entry set, for example, I have here some of the entries, for example, 1, 2, 2, 1, 3, 4, 2, 2, 1, 3, 1, 3. I reminds that 3, 1, 3 is third row, first column, third symbol. It corresponds to this cell. Okay, if I apply this isotopes, which I remind that the first triple, the first element of the triple corresponds to the permutation of the rows. In this way, I permute the first, I switch the first row and the second row, and the third row belongs, stay exactly the same. The third and the fourth, I have not writing here. The fourth, that's the fourth one. The fourth row is stay. Okay, I switch the first and the second row. In the second permutation, I permute the columns. So the first column goes to the second to the third one to the fourth one, and the fourth one to the first one. And the last permutation corresponds to a permutation of the symbols. So I permute, or I switch the first and the second symbol, and I permute the third symbol go to the fourth one to the fifth one, and the fifth one to the third one. Okay? So do you have some questions? Okay, so in this way, if I permute, if I use the triples of the entry set, for example, imagine this one, the first one, 1 to 2. 1 to 2 go each component by means of the corresponding permutation. So 1, according to the alpha permutation, goes to 2, 1 goes to 2. 2 goes, according to the second permutation, goes to 3, so 2 goes to 3. And the last component, which is 2, goes, according to the gamma permutation, goes to 1. Goes to 1. So the triple 1, 2, 2 goes to the triple 2, 3, 1. And 2, 3, 1 is the second row, third column, 1 symbol. So here you have that this entry in red, the first entry in red, goes to the first entry in blue. And the same with the rest of entries. Here you have an example, but you can check with all the elements, with all the entries of the partial Latin square, and you obtain the isotopic. It is called isotopic Latin square. So this is the concept of isotopes. And isotopes is like a symmetry. It's a symmetry of Latin squares. In fact, when you apply isotopes and you obtain the same Latin square, it is called an autotopes. So an isotopes becomes an autotopes when it preserves the partial Latin square under consideration. Here you have an example. This is a partial Latin square, and if you apply this permutation of rows, columns, and here, there is a font open. There is an open font. Okay, so here you obtain the same partial Latin square. It is called an autotope. Applications of autotopes. So you have an application, for example, this is of the partial Latin squares. Okay, here you have other applications to study incidence structures, to study graph coloring games, because every Latin square and every partial Latin square has a correspondence to graphs. So in such a way that the symbols correspond to colors of these graphs. Okay, there is an open phone in the audience. Okay, I hope that you listen me correctly. More applications. Here you have another application, which is pattern recognition. Partial Latin squares are used in cryptography. So here you have a possible application of isotopes, autotopes, to study pattern recognition in computer theory. And a final application that I show you is the enumeration and classification of this structure. Here you have, it's called Seminet. So you can use partial Latin squares by use and isotopes of partial Latin squares to study seminets. Okay, the concept of isotopes, the origin of this concept is was introduced by Albert in 1942. but not for Latin squares, but for algebras, in such a way that he said that two algebras, A1 and A2, are isotopic if there exists three permutations, three in this case they are non-linear transformation, non-singular linear transformations, but applied to algebras, in such a way that you this law of the permutation. You have that alpha x beta y is equal gamma x y. So if you think that alpha, beta, and gamma are exactly the same, you have alpha, 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 then you obtain what is usually called an isomorphism. So anisotopism is a generalization of the concept of isomorphism. This is for algebras, but 2 years later, Brooke introduced the concept of isotopism of algebra to isotopism of quasigroups, and it's exactly the same. But instead of algebras, he used the concept of quasigroups of Moufang. What happens that since the multiplication table of a quasigroup is a Latin square, so you can generalize the concept of isotopism of algebra to isotopism of Latin squares in the way that I have showed you before. Okay, the theory of isotopism has developed these first works of Albert and Brooke, and here you have a recent paper that we have in which we have showed this development. There are a wide amount of mathematicians who worked in this topic. So here you have, if you are interested, you can see this paper. Particularly in 2007, McKay, Miner, and Myhrvold introduced a way to compare or to be equivalent every isotopism of a Latin square with isomorphic colored graphs. Here you have an example, and if you are interested in this application, in this equivalence between isotopism and graph coloring, you have this. This is the paper. Okay, it is an interesting application. And they, in fact, obtain this theorem in which you can see that in order to study isotopism, it is only necessary to study the cycle structure of each permutation of the isotopism. What is a cycle structure? Is you have a permutation, for example, here, 1, 2, 3, 4, 5, 6, 7, 8, 9. This is the disjoint decomposition of a permutation into disjoint cycles. Okay, you have here 4 cycles, and you study the length of each cycle. Here, for example, you have a cycle of length 4, 2 cycles of length 2, and 1 cycle of length 1. So the cycle permutation in this case is 4, 1, 2, 2, 1. That is to say, you have 1 cycle of length 4, 2 cycles of length 2, and 1 cycle of length 1. So this is the cycle structure. If you have not a permutation but anisotopism, you have 3 permutations: the permutations of row, the permutation of columns, and the permutation of symbols. So the cycle structure of anisotopism is the combination of the cycle structure of the row permutation, the column permutation, and the symbol permutation. What is interesting is that the set of isotopism is only known for Latin square of order up to 17. Okay. For order up to 17, because the increasement of Latin squares is exponential, so it's very difficult to work with higher orders. For example, in cryptography, you need Latin squares of order 256, but you can see that even for smaller orders, and 17 is not a small order for Latin squares, but it's very difficult to obtain results for a rise, which we can think that they are easy to. Okay, these are the preliminaries of this talk, so let me start with the concept of critical sets based on Latin square autotopism. We have introduced before the concept of critical set, but now we are going to work with critical set based on Latin squares autotopism. So this is the concept. Imagine that I have an autotopism of a Latin square, of a partial Latin square. Here you have an example. This is a partial Latin square of order 4. Here you have an autotopism. You can check. In this autotopism, you switch the first and the second row, the third and the fourth row, the first and the second column, the third and the fourth column, and the symbols remain equal. You have here the identity, so the symbols remain exactly the same. So you can check and you can see that it is a symmetry of this partial Latin square. It remains exactly the same. Well, the interesting thing is that this partial Latin square is theta uniquely completable to that one. What does it mean? It means that it is uniquely completable, so you can complete it in order to obtain this Latin square, but in fact, theta is an autotopies of this Latin square. This is a trivial example, but because in fact this partial Latin square is uniquely completable. You can remove the theta. You can remove it, and this partial Latin square is uniquely completable. In fact, it's the same example of before. But imagine that we remove one of the array, one of the entries. So, for example, you can see that I am going to remove some of the entries. Well, the new partial Latin square is also theta uniquely completable. Why? Because imagine that I consider this entry, this blue entry. This blue entry corresponds to the triple second row, second column, and first symbol. So 2 to 1. This is 2 to 1. So if I apply this permutation to the triple 2 to 1, 2 goes to 1, 2 goes to 1, and 1 goes to 1 because it's the identity. So the triple 2 to 1 goes to 1, 1, 1. So keeping in mind this blue cell, obtain the left corner. The left corner, okay? So I obtain this other blue entry. So I have more information. Theta uniquely completable is more powerful than uniquely completable because you have more information. You have information about the symmetry of the partial Latin square. So you remind the concept of critical set. It is a uniquely completable partial Latin square, which is in such a way that if I remove one of the entries, then you don't obtain a uniquely completable. So we can't remove any of the colored cells. But a theta critical set is more powerful because I can remove entries in the way that I have shown you before. Here you can see that is the same example concerning the Latin square. The Latin square is exactly the same, but the partial Latin square, I have removed some of the entries. In fact, I have removed, the only entry that I have removed is the left corner, the left upper corner. Okay, I have removed it. But in fact, this partial Latin square is not uniquely completable to the Latin square, but is theta uniquely completable to the Latin square because what I have shown you before, no? Because this blue entry goes to this blue entry, so finally you obtain this partial Latin square. But moreover, if you remove another colored cell, then you obtain a partial Latin square which is not uniquely completable to the Latin square. So this is the theta critical set. This way to complete the partial Latin square in order to obtain a Latin square this is because it's mandatory that you obtain an entry corresponding to this partial Latin square. So, and a final concept, the concept of theta orbit. What is an orbit? Okay, we know that we can apply a permutation, an isotope, permutation of rows, permutation of columns, permutation and symbols in order to obtain more information about the symmetry of the Latin square. Okay, which is an orbit. An orbit corresponds to an entry. For example, you have here a series of entries. Each orbit corresponds to one of the entries. For example, the first one, the orbit of the triple 111. The triple 111 corresponds in this Latin square to this one. Okay, is the left upper corner. So this 111, according to this autotopes, 1, 2, 3, 4, 1, 2, 3, 4 entity, these red cells go to this red cell. And reciprocally, this second red cell goes to this first red cell. These two are connected. And in order to see it in an easy way, I have colored it in red. So these red cells correspond to an orbit. The blue ones correspond to another orbit, the green ones to another orbit, and so on. So here you have 1, 2, 3, 4, 5, 6, 7, 8 orbits. 8 orbits corresponding to this symmetry. Remember that this way of colored the array is because you can think on it as graphs. These problems you can go to graph and it's exactly the same. Okay, types of orbits. Not all the orbits are equal. This is important. Not all the orbits are equal. So, for example, here you have a classification of theta orbits. You have a theta orbit is called trivial if it corresponds exactly to one entry. For example, in this permutation, this isotopes, you have that the brown orbit is this right down corner. This brown entry correspond to the triplet 3, 3, 2, third row, third column, and second symbol, right? 3, 3, 2. So 3, 3, 2, if you apply the permutation, goes to 3, 3, 2. 3 remains equal, 3 remains equal, and 2 remains equal. So this entry remains exactly the same. So the orbit is composed by only one element, so this orbit is trivial. Other types of orbits, principal orbit. A theta orbit is called principal if it does have three components. For example, the red one. The red one, you have the triples 1, 1, 1 and 2, 2, 3. 1, 1, 1 and 2, 2, 3 doesn't share any components. So this red orbit is principal. And secondary theta orbits are orbits which contains two distinct entries with one common component. For example, row monotone orbits, the orange. The orange orbits share the row components. They are in the third component. All the entries are in the third component. So the orange is row monotone. The green one is column monotone, and the blue one is symbol monotone, because these orbits, all the components share the symbol 2. So finally, we have trivial orbits, row monotone orbits, column monotone orbits, and symbol monotone orbits. Moreover, two row monotone orbits are called parallel, and here you have an example with the orbit red and blue, if they share exactly the same columns and the same symbols. So in this red color, in this red orbit and blue orbits, you can see that these two orbits share the same columns and the same symbols. So they are said to be parallel. These are parallel row monotones, and exactly the same you have, or similarly, you have the concept of parallel column monotones. For example, the orange and the green are parallel column monotones because they share the same rows and the same symbols. Okay? Right. Which are the problems? There are three main questions. If you have a Latin square and an autotopies of Latin square, the problem is determine the exact value of the number of theta critical sets, which is the number. How many theta critical sets do you have? Another question, which is the size of the smallest theta critical set of this Latin square? And the final question, which is the size of the largest theta critical set of Latin square? The size is the number of entries, which is the smallest number of entries, which is the largest number of entries, and how many theta critical sets do you have related to a Latin square and an autotopies. The first lemma that we have, and which is interesting in order to work on this topic, is that all these values only depend on the cycle structure of the autotopies and the main class of the Latin square. So you don't have to work on the Latin squares, and you don't have to work through all the symmetries, to all the with all the isotopies, but only with those one having distinct cycle structures or distinct main class. Two Latin squares belong to the same class if they coincide up isotopies and permutation among the three components of their entries. That is to say, you can have two Latin squares or two partial Latin squares, and they are in the same class. If you can do anisotopies, you can permute rows, permute columns, permute symbols, and after that, you can change the role between rows, columns, and symbols. For example, imagine that you have the triple 2, 2, 3, and you change, or 1, 2, 3. You have the triple 1, 2, 3, first row, second column, and third symbol, and you do a permutation of these components. And you have, for example, instead of 1, 2, 3, you have 2, 1, 3. 2, 1, 3 is a transposition. You transpose rows with columns. So if you do this change of the rows, column, and symbols, and you do an isotope bins, you obtain another Latin square or another partial Latin square, which correspond to the main class. In such a way that, for example, if we fix the order, smaller orders, for example, order less than 2 or equal to 5, here you have the main classes of Latin squares of order up to 4. You have 4 possibilities. You have only one Latin square, only one main class of Latin square of order 2, only one main class of a Latin square of order 3, and 2 main classes of Latin square of order. With order 5, you have another 2 main classes. So if you need to work or need to study in these main questions, number of theta critical sets, size of the smallest, and size of the largest of order up to 5, you have to study these 6 Latin squares. In fact, in these tables, you have the solutions. Okay, in this table, you have the Latin square, you have the isotopes, you have the cycle structure. For example, this one correspond is order 4, so you have cycles of order 1, 1 cycle of order 2, for the rows, for the columns, and for the symbols. So you have in this column the cycle structure. You have the number of theta critical sets, you have the smallest size of the theta critical sets, and you have the largest size of the theta critical sets for order 4, for order 5. So in the minutes that I have still for the talk, I am going to show you how to obtain some of these numbers. For example, some preliminary results. We have trivially that the smallest size is less than or equal to the larger size, and this number is less than or equal to the number of orbits. Why? Because, for example, in this example of order 2, which is trivial, if I know one element of an orbit, for example, this cell, which is 1, 1, 1, I know, according to this permutation, according to this isotopes, that 1, 1, 1 goes to 1 goes to 2, 1 goes to 2, and 1 goes to 1. So the triple 1, 1, 1 goes to 2, 2, 1. So if you have one information or an information about one of the entries of orbit, you know, of a theta orbit, you know all the information, all the entries of this orbit. So you need only, at most, you need one entry of an orbit, okay? So the largest size of a critical set is at most the number of theta orbit. So in this case, the largest critical set, the size of the largest critical set is at most 2, but you can check in an easy way that it is only necessary one entry. For example, if you check, you can check if you consider the entry 1, 1, 1, so you can complete like a scoop by 4 set entries, and you complete all the Latin square of order 2. So finally, these two numbers, these two sizes are 1, and the number of critical sets coincide with the number of entries, which is 4. This is a trivial example. Another results, if there exists m secondary parallel theta orbits of the same time, then every theta critical set contains at least m-1 entries. So you have this formula. Example, you have a Latin square of order 3, this isotopes, or this autotope, and here you can see that I have 3 parallel symbol monotones theta orbits. The red ones are symbol monotone, or is symbol monotone, because you have 1, 1, 1. The blue one, you have the symbol 2, 2, 2, and the green one, you have the symbol 3, 3, 3. So all of them are monotone. So you have 3 parallel monotones, symbol monotones orbits. So according to this proposition, m is 3, 3 minus 1 is 2. So you have this result. 2 is less than to the smallest size. In fact, the largest size is smallest than to 3, or equal to 3, because you have 3 orbits. So you have this first approximation. In fact, you check that with only 2 entries, you can obtain a critical set. And in fact, the number of critical sets is 27. More examples. You have another results in which you say that if the gamma permutation, that is to say, the symbol permutation is the identity, okay, the third permutation, which is the permutation corresponding to the symbol, the identity, then you have these two formulas. The smallest and the largest critical set, the size is n-1, and the number of critical set is n power n. This is the case of the two previous examples. The two previous examples, the autotopies, the permutation, the symbol permutation was the identity, and you can see, you can check, and they coincide with the formulas that I have shown. If you don't have the identity in the column permutation, then you have another gains, another possibilities. In this example, you can check in this case that any of the entries of this Latin square of order 3 correspond or give rise to a theta critical set of order 1. So in this case, the smallest and the largest critical set size are 1, and the number of critical set is 9. All these examples are easy to check, so I am going to see it in a faster way. So here, for example, you have Latin square of order 4. All the orbits are colored in the same way, okay? Here you have 4 orbits. One of them, for example, the red one is symbol monotone. The blue one and the green one are not principal because they share symbols, but you can play in a similar way, in such a way that in this case, every theta critical set of order 2 contain one entry of a symbol monotone orbit. In this case, you have a symbol of the red orbit or the orange, or you have only one. It is only necessary one of them, but you need it. You need one of these entries, and one entry of a non-monotone theta orbit. That is to say, you require one entry of a red or an orange orbit and one entry of the blue or the green entries. You can check, and with only these 2 entries, you recover the complex Latin squares, and you have these values. This is another example, in this case with order 5. Okay, I'm going to see more examples. There are another kinds of autotopies in which you can impose exactly one trivial orbit. For example, in this case, a Latin square of order 3, and these autotopies, you have that the third row is preserved, the third column is preserved, and the second symbol is preserved. So if you have this pink entry, which corresponds to the triple 332, third row, third column, and second symbol, 332, 332 goes to 332. So this is a trivial orbit. Well, when you have only one trivial orbit, it is not necessary to have it in the critical set, because you have only one, and this is the only possibility. So it is not necessary to have to be in a theta critical set. So you can remove of a partial Latin square. You don't need it. In such a way that in this case, knowing it, every theta critical set contains exactly or one entry of the principal theta orbit. Here, the principal orbit is the 2, is the blue one. Sorry, is the red one. Is the red one. Okay, the principal is the red one, because you don't have any share of rows, columns, and symbols. So you need or one element of the red orbit or 2 entries of 2 distinct secondary theta orbits. So you consider or only one of the red one, or 2, and these 2 maybe in the blue, in the green, or in the orange. Okay, not 2 in the same one, because with only one you have all the entry. But for example, one on the blue and one on the green, you recover all the Latin square. So you have here examples of theta critical sets. You can check like a Sudoku, and you finish it. Okay, here you have more examples. Okay, maybe I am going to finish with this last example, in which it is a bit more difficult. No? In this case of a Latin square of order 5, you have these autotopies, so you can color the entries according to the corresponding orbits. So you have row monotone orbits, column monotone orbits, trivial orbits, which is the pink one, symbol monotone orbits, which is the cyan orbit, and the other ones are not monotone. In fact, they are principal, because you have, for example, the green one is which are the symbol. The symbol are 1, 2, 3, 4, and they don't share neither or either rows, neither nor columns. So you have principals. So the green one, the orange, and the blue and the yellow one are principal orbits. Well, you can check that every theta critical set must contain at least one principal theta orbit. Why? Because imagine that you have a partial Latin square in which a candidate for theta critical set in which none of the entries of a principal orbit is taken. That is to say, I don't take green ones, orange ones, or yellow ones. So you have only these colors ones. You can take 1 or 2 or what you want, but neither in the green, in the orange, or in the yellow. So you have here an example of another Latin squares in which you can complete your candidate. Okay, this Latin square is different of the previous one, but if you consider one of the red, the cyan, or the blue, even the pink one, you can complete to this another Latin square. So your candidate is not a theta critical set. So every theta critical set must contain at least one principal theta orbit. And in a similar way, you can check that the knowledge of only one principal theta orbit is not enough. That is to say, if I consider, for example, all the green principal orbits, then you can obtain a Latin square which is different of the original one. So these two Latin squares are the same, but they share the same principal orbit, the theta principal orbits. So every critical set has contained more than one in a principal orbit. Moreover, the knowledge of only a principal theta orbit and other distinct non-trivial theta orbit is not enough. Okay, you can say, okay, I take, for example, one of the green and one of the red. You have here an example of another completion different of the original one. And here you have examples in this regard. So you have these requirements in order to obtain a theta critical set. Finally, if you put all this information together, you can check that every theta critical set of this Latin square, according to these isotopes, have size 3. So you need 3 entries. And these 3 entries can be taken from, in this way, 3 distinct principal theta orbits, 2 distinct principal theta orbits, and the symbol monotone theta orbit, or a principal theta orbit and 2 distinct secondary theta orbits. With these 3 possibilities, you can do the computation, the corresponding computation, and finally you obtain these values. Okay, so I have shown you some of the examples to obtain the different elements that we have seen in the tables that I have shown you before. I have only shown you the easiest one. There are other ones which should require more technical results, but at the end, I am going to show you the paper in which this talk is based. If you are interested, you can see it, and of course, you can ask me after or by mail. And if you are interested, I think it's an interesting topic. In fact, there are a lot of open questions, so I'm going to show you some open questions in order to finish my talk. So, some open questions. What is the computational complexity of deciding whether a partial Latin square is theta completable? It is. Until now, it is not studied, so the computational complexity. More question. Does a theta critical set of size m exist for every m belonging to the interval between the smallest size and the larger size? Another question. Find lower and upper bound, not for a specific Latin square, but in general. In general, if I have any Latin square of order n, which is the smallest size of a theta critical set, and which is the largest size of a theta critical set, because until now the results are for a specific square. But which are for any general Latin square of order n having theta as an autotopes, which is the smallest and which is the largest? Another question. Is it possible to find some general formulas of all the values that we have asked for before for some specific cycle structure? Because if not, you have to study each cycle structure continuously, and these are for Latin square of order up to 5. But for higher orders, it is very difficult. So is it possible to obtain some general formulas? It is also an open question. And a final open question. Until now, in this talk, I have shown you, I have introduced you different types of theta orbits: principal, row monotones, column monotones, symbol monotones, but they are not the only ones. There are only other types of theta orbits. For example, in this Latin square of order 6, you have different orbits, and none of them are principal or row monotones or symbol monotones, or okay. So you have another kinds of orbits. So they are not studied, and they exist for order higher than 5. And until now, the only order that we have studied is until 5. So this case is very curious, because this Latin square of order 6 is very symmetric. So and when you have more symmetries, more difficult is the more symmetry you have, the more difficult is the problem. So in these cases, how many types of non-monotone orbits exist, and what is exactly the role played by each one of them in the construct of theta critical sets, and which is the role of each one. Well, here you have some references corresponding to this talk. Particularly in this blue reference, you have the which this talk is based. It's a recent paper. It has been published very recently, and that's all. I thank you very much for your attention. I remain at your disposal for any question that you have. I hope that you have enjoyed it. For me, it's very, very interesting, this topic, because it's not difficult to understand it, and there are a lot of open questions. So I think that in a future, you have here the possibility to work on it, and obtain more results, and with a lot of application in cryptography, in pattern design, in combinatorics, in algebra, because you can change to quasi groups, and okay, so there are a lot of applications. So thank you very much for your attention, and I remain at your disposal for any question that you have.
Participants, if you have any queries, you can proceed now. Please post your queries in the chat section. I repeat, participants, if you have any queries, please post in the chat section.
Okay, thank you very much. I'm going to leave. Thank you, everybody, and thank you the organizers for inviting me to this talk.
Thank you, sir,
Bye.
for your opening speech. Now I call upon Dr. C. Sir, Assistant Professor, P. Research Department of Mathematics, Kongunada Arts and Science College, to welcome and introduce the speaker of the session. Sir, please.
Thank you, MOC team. To me, this task of introducing our guest of honor and speaker is a great privilege. I feel really happy to introduce my friend, Professor Dr. A.S. Nizar. He received the doctoral degree from Aligarh Muslim University, Aligarh, India in the year 2011 with the scholarship provided by the Central Government of India. He is currently working as Professor of Applied Mathematics, College of Arts and Sciences, Prince Satam bin Abdullah University, Saudi Arabia. He is a recipient of Riemann Young Researcher Award, PSEAU Research Excellence Award in the 2018 and 19 for the Best Researcher, a Distinguished Research Award for Outstanding Publications in the year 2017 and 2018 from the Prince Saddam bin Abdullah University, Saudi Arabia. His area of research interest is fractional calculus, mathematical modeling, special functions, machine learning, artificial intelligence, etc. He has served as invited speaker in the various international conferences and international seminars. He has completed around 8 funded research projects, written 4 books, and published more than 400 papers in reputed international publications, which is indexed in SCA, SCIE, and Scopus. He is an editorial board member of prestigious international publications, Associate Editor, Alexandria Engineering Journal, Elsevier, SCA Index Journal, and Mathematical Problems in Engineering, SCIE, Hindawi Publications, and Crystals, MDBI Publications, Progress in PE in Information Science Letters, and he is a special issue lead guest editor of various reputed journals. Sharing knowledge is the most fundamental act of friendship, because it is a way you can give something without losing something. So I invite my friend Professor Dr. Nizar to deliver the speech on the title of Fractional Order Mathematical Model of Novel Coronavirus Disease. Thank you all.
Thank you very much, Dr. Ravi, for a nice introduction. And thank you very much for the organizers for inviting me this conference as an invited speaker. So I am very humbled to present my knowledge with you, in front of you. And instead of wasting time, let me start the presentation here. Okay. I think you can hear me clearly.
Yes, sir. Audible, sir. Clearly.
Okay. Okay. Okay, let me start. Today, my focus is on fractional order mathematical model of novel coronavirus disease. So I would like to present the importance of mathematical modeling and how we develop a different type of concept using this fractional order calculus. Actually, we know this is very popular in recent days in many applications, like engineering, science, and other disciplines, including economics, many more fields. Because there is a memory effect if we are using the fractional operator, or if we are considering the point of view of engineering, you will get to 2 more parameters to tune the system. As compared to the ordinary derivative, the fractional derivative have many advantages. Okay. So today I will not make you bored. I will just take 30 minutes just to motivate you. So this will be a simple presentation, and I am sure that you will get some motivation from my presentation. So let me start. So the outline of the presentation is the fractional calculus. I will just say something about the history, then some facts on fractional order calculus, mathematical model of coronavirus disease 19, and some future work suggestions, and some observations on mathematical modeling with fractional order derivatives. Now you can see, as you know, the fractional order calculus as old as integer order calculus. It was born in 1695 when a law hospital asked the question to Leibniz, what is derivative if the order is half? Then it will lead to a paradox from which one day the useful consequence will be drawn. So you can see the question is very simple. If we are considering the order is half or any other fractional number or complex number, then what will be the answer? Okay, So this fractional calculus as old as the integer calculus, but it is delayed due to some reason. Okay, the reasons are, and let me explain or show you the developments of fractional calculus. Leibniz in 1695 contributed towards fractional calculus. After that, Euler, Lagrange, Laplace, Fourier, Abel, Leverly, Riemann, Capito in 1967, and very recent, Capito Fabrizio and Atangana Baleno. So usually the people, those who are working with, there are many more than 15 or 20 definitions are available in the literature with many generalization, like there is a Hilfer fractional derivative, many more derivatives are there, fractional concepts are there. But most popular, those who are working in this field, they are familiar with the Riemann Leverly, Capito Fabrizio, and Atangana Baleno. Okay, so these are the developments. So you can see now some facts on FOC, fractional order calculus, why it is delayed in applied field. Its application in engineering were delayed because the fractional order calculus has multiple definitions. I told you that there are more than 15 definitions for fractional calculus. And it's not a simple geometric interpretation. Okay, so you can see in the ordinary calculus, you can say that the rate of change or slope of the tangent, you can easily visualize these things for integer calculus. But here in the fractional calculus, there is not a simple geometric interpretation. And the first look, integral order calculus seems to be enough to solve the engineering problem. Okay, so the people are attracted by the integer order calculus because in the first look they can manage all the parameters by modeling with integer order calculus. However, many natural phenomena may be better described by fractional order calculus formulation because it takes into account the past behavior and it is compact when expressing higher order dynamics. That means past behavior means we can say the memory effect. Okay, that is very important in applied field to consider the memory effect. That's why the fractional order calculus is very popular with the recent researchers. Now, reason for fractional order calculus unexplored in applied sciences. There are some reasons. First of all, it has some inherent complexity. The fact that it does not have a fully acceptable geometrical or physical interpretation, and the apparent insufficiency of the integer calculus. You see, that means integer order calculus was dominant in the field because of these reasons. But gradually, reasons for fractional order calculus accepted by and engineers because it can describe the behavior of real dynamic systems in compact expressions considering the non-local characteristics like infinite memory. For example, you can see if you want to model the love between humans, it's highly dynamic, and like the fluctuations in the share market, or we can say the chaos in the share market, and the weather analysis. So there are a lot of applications with highly complex dynamical system, or we can say that the infinite memory, like phenomenon. Is this fractional order is very useful to model the problem. So I am just bringing the basic ideas how we are connecting this fractional order to the real world problem. So these are just just to familiarize you with the importance of fractional calculus. Now let me discuss with you one recent work about the mathematical modeling of coronavirus. You know that this COVID-19 is almost, you can say, the 1 year or more than 1 year. So, and you can find many mathematical studies are related to COVID-19. So in this light or in this flow, we also did many work in mathematical modeling of coronavirus. So let me explain this. Means what we did at the very beginning of coronavirus disease. Abstract here. So what I would like to present, the coronavirus disease is likely to emerge as a watershed moment in the history of the planet. As you know, it is going uncontrollable. COVID-19, the abbreviation of coronavirus disease, is caused by the severe acute respiratory syndrome, coronavirus 2, that means SARS-CoV-2, hit the globe with a bang. That you are reading, you are facing this struggle, or you can say that everything is collapsed with a lot of issues. And in December 2019, the first outbreak was noticed in the Hubei province, Wuhan, China. On 30th January 2020, the World Health Organization revealed the COVID-19 to be a public health emergency and identified it as a pandemic on 11 March 2020. So this was the history, as we are living in this era and we know everything about this virus. Now the symptoms of COVID virus, that also you are familiar with, it's not specific, and many cases showed that the infected person might be asymptomatic. Okay, that means some people are get affected but unable to identify. The COVID-19 virus spread to a large extent between the people in close contact with each other within approximately 2 meters. The common incubation period range from 1 to 14 days. All the things, how we are considering the data to model the problem. Okay, this presentation or this talk is focused on the mathematical modeling of coronavirus disease 19 with the different aspects. Main objective is to show the various of modeling with fractional operators and their impact on society. So you can see all the original result is considered here to prove how this study is impact on the society. So let me start with the motivation. So let me talk about the mathematical model. The application of computational mathematical methods to be numerically simulate infections with the population. Mathematical models of infectious disease dynamics have a deep history of more than 100 years. So all these, mathematical things are not very new, old, but the use of new fractional operators is new. The most common mathematical formulation which represent the individual transition in a community between compartments which attract the situation of individual infection to surprisingly significant insight. So these are some explanation about background of the study. These models of compartmental disease segregate a population into groups depending on each individual's infection and related population size with respect to time. Now you can see the coronavirus model. Lin et al. Suggested a conceptual model for the coronavirus. You can see this is a 1-year-old problem. So this is, say, that very recent, which was effectively catched the timeline of COVID-19 outbreak. Okay, a mathematical model for reproducing the stage-based transmissibility of a novel coronavirus is examined in 2. That means Chen et al. So there are some papers are available. So our motivation is, one paper was published in Alexandria Engineering Journal by Han and Tangana, and they formulated the mathematical model of coronavirus versus people which given as. So this model was available. Now you can see there are 2 types of modeling. Once you have to collect the parameters and you have to model yourself the problem. Okay, but for us, in front of us, this model was available, and this was published in Alexandria Engineering Journal with mathematical modeling of coronavirus, and they consider some data from China. Okay, now what we did, so some parameters are here. You can see that here n is the total population and all. So here the parameters are used where n represent the total population of the people. Further, n is segregated into 5 subclasses such as susceptible people, exposed, infected, asymptotically infected, and the removed or recovered people. The people in the severe or market are denoted by QT. the description of various parameters used in this model with their values are reference given in the following table. This table is given in the last slide after my formulation. So you can see this is our motivation. Okay, we got a model from the literature, and we model this. You can say that by considering some data from India, and we model with the fractional operator. Now you can see here in India on 11th March, you can see our observation is at the very initial stage. Okay, by considering the corona cases in India on 11th March 2020, the Indian government start taking strict action by suspending all the visas to India with the effect of 13th March 2020 till 15th April 2020. So the first case is reported a 76-year-old man, the first victim of COVID-19 in the country, who had returned from Saudi Arabia on 12th March 2020. Now you can see why I am explaining all these things, because we need such information to model the data. On 15th March, the confirmed cases were 100, but it is close to 1,000 on 28th March and 2,000 on 2nd April. So you can see in India at the initial stage, very few cases were there, but immediately start increasing the cases. So we observed this and we suggested some control measure, how to control this with the help of mathematical modeling. The Indian government has implemented high measure for moderate outbreak. A day-long countrywide public curfew was observed in India on March 22. Moreover, on March 24, the Prime Minister of India announced a countrywide lockdown for 21 days. So in this study, we considered the reported cases of SARS-CoV-2 from March 14, 2020 till March 26, 2020. You can see the first cases reported in India, or we can say declared on 11th March. And we considered the data from 14 to 26. That means this study was performed very early stage of coronavirus in India. Now you can see the graph is given about the confirmed cases of India in that time period. So now you may have the question why we are using the fractional derivative, because the mathematical model utilizing ordinary differential equation within order have been demonstrated significantly for understanding the dynamics of biological systems. But in any case, every single such model depends on the classical derivative that have some limitation related to the order of differential equations under consideration. Means if you have parameters, means you can tune the system more easily. In fractional, the differential operator used are non-integer or fractional, which is summary and are valuable to demonstrate natural phenomena, nature-related truths and facts having non-local dynamics and anomalous behavior. So this is the reason that people are coming with the fractional modeling. The study of epidemiological process involving memory is appropriate for such a phrase rely on memory, which is fractional derivative operator. So these are some of more. Now, what we used here, we used the one of the recent fractional operator that is called the Capito-Fabrizio, or we simply called it as CF, has recommended a unique fractional derivative operator and so the need to examine the properties of it's this operator. So in Capito-Fabrizio, the kernel is exponential, and after that, Atangana and Baleno came with the Mittag-Leffler kernel. But we used this. It is depending on the complexity of your problem. The advantage of this operator is that it has non-local and non-singular kernel, and best suitable to describe and analyze the dynamics of COVID-19. More literature on Capito-Fabrizio derivative is given in the references. Now you can see, motivated by the above useful application of the Capito-Fabrizio operator in epidemic mathematical models, here the dynamics of novel COVID models suggested by Khan et al. in the form of system of nonlinear differential equation involving the CF fractional derivative. So I told you that we have a model already available in the literature. So we model that one with the CF derivative. You can see here the model. So what we did, we developed the proposed model into the characteristic disease and in terms of the capital Fabrizio fractional coefficients to find a condition that how to minimize and control novel corona disease spreading in the community. You can see using the mathematical model, the mathematicians or the researchers are trying to suggest some control measure to the government. And we successfully suggested. I will explain more about that in one of other paper. We gave some control measure how to control this spreading very easily with the help of mathematical modeling. So these mathematical models also have the impact on the society. Finally, all the theoretical results are verified with the help of simulation. Now you can see here, this is our model. That means here we use the CF fractional operator that's called a Capito-Fabrizio fractional derivative. Which you can see here we use the fractional order of tau. And I told you that this model is simply derived because you have already a model. Like you can see that if you consider Tyler and then you will get yes, you already have a model in the literature, so you just have to apply the fractional concept here. Now you can see from this fractional model what we did. We used the method to approximate the solution and the graphical result by iterative Laplace transform method. So recently many people applied the different method. You can see you have to just check whether you are getting better result or not. So here we combined the Laplace transform with the NIM. That method, we can say that iterative Laplace transform method, we used this technique to solve the. So what we did in this paper, the findings are we consider the stability analysis of proposed method first. Then we discuss about the stability analysis and the equilibria or of equilibria. To determine the condition for control the novel coronavirus disease, we analyzed the qualitative behavior of the proposed model and then calculated the basic reproduction number. So if you go through the model papers, you can see that there is a reproduction number called R0. So usually you are solving all these things like stability, existence, and uniqueness. So there is some procedure or there are some procedures to solve such type of papers. So the behavior of equilibrium is studied by using nonlinear stability analysis and observed whether the equilibrium becomes stable and the disease outbreak will be under control. So you can see if you are familiar with this mathematical modeling, then you can understand that why we are using the stability analysis. So I am not explaining all the expression here because it's a long procedure and it needs more time to explain. So I am just sharing with you the main content of the paper and the importance of the study. So in the third part, what we did the data fitting and numerical simulation. Here we study the numerical simulation of the CF coronavirus model. For this, we consider few parametric values from the literature and remain are estimated or fitted. We use the total initial population of India, capital N, and we got this data from the Ministry of Home Affairs. It is Home Affairs, Government of India, with this website. Now you can see I told you that we use these parameters like a description of the parameters here. Here we consider the birth rate and it's estimated, and you have the contact rate, that means alpha, and we have the reference for the natural mortality rate, that is lambda. So all these parameters are mentioned in the model, and transmission rate, incubation rate, incubation period, and the proportion of asymptotic infection, these things are fitted. And recovery removal of rate, that's taken from reference 3. and the contribution of the virus Q by is fitted, removing rate of virus from Q is fitted. So, there are many technicality. So you have to understand this thing. If you are going to model a problem, then you have to understand how to choose the most suitable parameters. Okay. Now, using this, now you can see all these parameters are used in this model, and the explanation is given in the table. Okay. Now here you can see the delta, you can see here alpha, beta. So all these parameters are clearly mentioned in this. These things are available, and you can use any other different operator, fractional operator, to model the same problem, and you can use the different transform technique like a wavelet transform, Sumudu transform, something like that, and you can check whether you are getting more improved result or not. So there are a lot of chance or lot of scope to extend this type of work to the new work. And other thing is that I told you, nowadays, there are different type of cases with the coronavirus. Infected person is recovered, again infected. So there are many things, many dynamics are there. And vaccinated person is again getting coronavirus. So, the selection of parameters still possible, but there are a lot of problems are pending in this. The model consists of many parameters. So you can see, because initially we did this work, so we face several problems. Okay, several limitations are arising steady, because now this is the model related to Indian data, a fraction model related to Indian data. So you face a lot of difficulties to manage the model. Firstly, we have not used the data of COVID because it's a short period of time for the session, whereas as utilized that the literature. So that's the limitation for initial study. Besides, the parameters of population were not from a precise data, because if you will take a huge data set or data set, then you can get the better results. There are these small parameters of our model. This would translate into opportunities in industry. So if you have some limitation, the model you have to rely 100%, but if that's 80% or 95%, you can rely on this model. Increasing capacity of testable COVID-19 lead to getting clear information on the number of asymptomatic cases. These are our, we observed this thing at the time of our paper. This will enhance the study of and further. So we listed all these things in our discussion, that if you will take the large data set, then you can model the things very clearly, and you will get the accuracies better if you consider different cases, and also you can say that the testing capacity must be increased and all this. Okay, we suggested many things. The government of India has imposed a 21 days nationwide lockdown from 25 March 2020 and asking people to stay at home, restrict population movement, which can help the limit transmission of the virus. So according to our study, we also observed the same. This lockdown was very important, and we conclude that the restrict population movement, which can help to limit the transmission of the virus. So all these things are not writing just like a sentence, or not saying just in a flow. All these things are proved by graphical and simulation analysis, we can say. So here you can see some simulation analysis we did for the fractional order, the dynamical behavior of suspected population and exposed population for various values of fractional order tau with respect to time. So from this observation, all that conclusion arrived. Okay. So, and after that, what we did, we plot the graph for the dynamical behavior of infected population and asymptomatic population for various values with respect to time. So we did many observations for this actional model. After that, the dynamical behavior of recovered population, okay, and reservoir population QT for various values of flow time. We observed that the recovery getting into or not, then it's very initial stage at the last. So this model can improve if we are considering the recent data, or you can say if you consider what data and you all these things, how many of the recovered person again get affected, or the many see the dynamics of coronavirus is unique, and sometimes even the second stage of, or you can say the second inning coronavirus, it is second phase of virus change. Some genetic issues are there, and also you have to study about that also. What's the problem? Why it is change such of such type of changes are, so many things are there, and big model okay. You see this paper we very quick paper at March, and the paper we submitted in April form, and it is published in April. So very easily we started, we use our data, we did recommendation to government, and the following end of COVID-19 and absence of vaccine we are able to predict result is vaccine because at the beginning 1 year before the early COVID-19 pandemic, and the sure treatment like preventive measure to reduce the coronavirus is recommended. Preventive measures, that social distance, and that so like this, mask and things recommended very beginning, almost 1 year. So social distancing of contacts of mitigate containment, suppress against the infection, all this very beginning. Moreover, the policy of the transmission finding and isolating patients for quarantine phase of the power would be down towards the infection. So we are do like isolating the infected person as quick as possible. But we suggested this through our study in the last April 2020, and this paper we posted in the preprint, and after that, fortunately, we got this paper accepted in a good journal also. Now I won't take much time to conclude my talk within 5 to 10 minutes. Okay. So concluding observation. So in this paper, we proposed the pandemic problem of COVID-19. We formed a fractional model to suggest possible control strategies that will be helpful for public health officials. A mathematician, if you collaborate with some medical person or some medical, will very helpful. Mathematical model is testing things with the help of analysis. You can say the simulation analysis, numerical analysis, whatever. So if we can do this much, means if you collaborate with the medical personalities, means we will get the real information with real data. It has been observed from the present work that the infectious fractional derivative operator. Moreover, the fixed point theory, the stability criteria for steady solution and existence have been verified. You know that in the modeling problem, we study this existence and uniqueness and stability, all these cases. So we will take the help of fixed point theory. Approximate solution and graphical demonstration by using iterative Laplace transform method of Fabrizio fractional coronavirus model have been presented. It is not that the memory features in CF. It explores hidden dynamics of the infection in the mathematical infectious disease. So why we are using this fractional derivative? So this is one of the reason. The memory effect of the fractional derivative means like CF and AB derivative explore the hidden dynamics of the infection in the mathematical model of infectious disease, which is not possible to find with the integer of derivative. So you got the answer why we are using model of integer model, and this is one of the reason we are interested to use the fractional order. Now you can see. Okay, let me continue. It would be noted from this analysis that one of the very key parameters of the disease transmission coefficient, that is gamma, which precisely determine the basic reproduction number R0. So there are R0 depending on R0. You can see any more paper. You can see the production. The control measures suggest that the infection will be eradicated rapidly once the control strategies will be implemented in a manner. So you can see these things are from leaders and experts every day. You can say their talk. You can say information. So we searched the same from this mathematical model. And in the end, all the theoretical results are supported with the help of graphical and tabular representation by using mathematical software. This model became highly reliable when real-time and actual estimates of transmission structure are available. So you can get the data or the real data with the government approval, or you can nowadays because we have a website there and everything is clear there. So that will help to model more reliable things. Now you can see suggested work direction. Okay, in the future we study the dynamics of COVID-19 along with the effect of some control measures by including more classes into the present model. So I told you that there are a lot of things nowadays happening related to the COVID-19. So you can consider all these things, like recovered person is infected again. So there are many things. Okay, these compartments include symptomatic but not tracer population. You can see asymptomatic and quarantine individuals. The model will be extended and post memory features and non-locality. And recently I found that many people did work in this direction. Even we did many work in this direction. So just to motivate you, I want to show some more work and I will stop. Okay. So more papers on COVID-19 by myself and my team. So this is the first paper. I told you that the same paper I discussed with a mathematical model of COVID-19 using fractional derivative outbreak in India with the dynamics of transmission and control. So this paper available in the published version is available in the literature. With more information, you can refer this paper. So after that, immediately after that, we found that we can improve our paper by considering many things, more parameters. Then we wrote another paper called Analysis of COVID-19 Pandemic Spreading in India by Epidemiological Model and a Fractional Differential Operator. You can see we consider more data, and this paper submitted on 15th May. So the first paper, April, after 1 month. So we took more data for this. for this study. And the interesting thing is that here our study is recommended more things. See here, a specific recommendation is there, that is I highlighted in blue color. So I will explain what is that. What we did in this paper, the iterative scheme to find the solution of the above model using Laplace transform and new iterative method, NIM. This is available in the literature. Stability criteria by using fixed point theory, along with Picard's successive approximation. Data fitting and estimation done along with the numerical simulation for various values of fractional order and displayed it graphically. We observed that the memory features of CF, again we used here CF, to explore hidden dynamics of the infections in the mathematical model, which not possible to find in digital. I already explained that. Now see, the most interestingly, the point 5. From the graphical analysis, it is observed that the 45 continuous days of lockdown can control COVID-19 effectively. So from this study, we recommended that if the government can implement the lockdown for 45 days continuously, then we can control the COVID-19 very effectively. Now you can see we are not the medical expert, or we are not the expert, those who are working related to prediction. For example, they can predict very easily based on the data, but this mathematical formulation or mathematical modeling, we suggested that the 45 continuous days lockdown can control the COVID-19 effectively. We tried to share our observation with many governmental agencies, but unfortunately, I think very few are noticed. But there was no much care about this study. Otherwise, this suggestion may be useful that time. But anyway, we did our work, and this paper also was an online at May, okay, and it's also available. Now, to motivate you, I have to share more papers related to this. So here you can see paper 3. This is with my friend Ravi, and he is also the organizer of this conference. And here what we use, here we used the Mittag-Leffler kernel, means the fractional derivative with the Mittag-Leffler kernel, that is called Atangana-Baleno derivative. So here also we did the mathematical model for spreading COVID-19 virus, and we did some observations. Here I am not going to into the detail, so because I think I have to wind up after 10 minutes. So let me finish it quickly. And another paper is about, you can see, numerical simulation and stability fractional order dynamic of COVID-19. This is published in this month, January 2021. So here also we consider fractional order models. Okay. So there are many papers in this direction. Paper 5, this is also the same month. Mathematical modeling to assess the imposition of lockdown during COVID-19 pandemic. So you can here focusing on lockdown, imposition of previous numerical session and stability. Here we did stability analysis. We studied about the lockdown of COVID-19. So there are a lot of options to continue your study with the modeling. I consider different steps of, there are lockdown, there are something we are called isolation strategy, okay, and we can say that vaccination. So many points you can consider in your study, and you can see the paper 6. It's also very recent paper. So here what we consider the real data, and we use the capital fractional derivative to model the problem. And this is also published. It is also published very recently. So another one you can see that if you can collaborate different people and can consider the data of different country. So here we did the fractional order mathematical model, and here we use the Mitya-Glover kernel that is called Atangana operator, and we consider the data from Nigeria because the collaborators from Nigeria. So we consider the things and we analyze the data of Nigeria there in this paper, and it's published in Q1 Journal of Impact Factor 4.89, and this is also published very recently. And after that, this is now there is no fractional derivative, but this is an analysis of social distancing, quarantine, restriction, etc. See, there are search options. So you can say a team or collaborators all situation this COVID, like here lockdown, and you see here data from the different country, and here social distancing, quarantine strategy, etc. And there are many more papers are there, but I am not going to show you everything. These are the references. I told you that three was the important references for us. Modeling of dynamics of novel coronavirus with the fractional derivative. That's published in Alexandria Engineering Journal. And there are some Capito Fabrizio, that new definition of fractional derivative. You can see 8. This is available, and some of our papers also available in the literature related to you can say that the application of CF model. So before concluding, let me show you something to motivate you. So always I believe that the research motivation, the limitation is your imagination. So dream it, wish it, and do it. Great Albert Einstein, the imagination is more important than knowledge. So imagine yourself and let's set and go, dream it, we can do it. And finally, I would like to wind up my talk with a proverb, that's African proverb. If you want to go fast, go alone. If you want to go far, then go together. So that's the importance of teamwork. If you want to go far, means go together. Means you have to plan, you have to share your ideas with the different group. If you are a mathematician, you can discuss your idea with the medical personalities, engineers, so that you can model the new problem, and they are expert in the applied field. We are expert in the analytic and numeric field. So together we can do many things, and that is the success of my research. That's why today I published more than 500 papers with joining good group and discussing the things to good group. So remember this proverb: if you want to go fast, go alone. If you want to go far, go together. And I hope you like this presentation, and thank you very much.
Participants, those who have queries, please ask, or you may post it in the chat section. Ms. Logeshwari has asked this query. Can we use the Riemann, Loewy, and Capto derivatives for the mathematical COVID-19 model, sir?
We can use any fractional operator, there is no problem. But you can see the operators have memory effect, like Capito Fabrizio, Atangana. So the this memory effect is very important. That's why these new fractional derivative operators are developed by considering this important property. So that's why the impact will be less. You can model with any fractional operator, no problem. But if there will be a question about the memory effect, then any model with the new fractional derivative will be welcomed more.
Any other queries? One more query we have, sir. Can we model the problems with the infinitesimal generator, sir? Jyotimani ma'am has asked this. Can we
You can
model the problems with infinitesimal generator?
you can see this is depending on your data. Yeah. If you are, for example, some data you can see that it is depending on the complexity of your problem. If you feel that okay, it is sometimes we are modeling with the stochastic modeling, sometimes we are using fuzzy modeling. So this type things, why? Because it is depending on your model or your parameters. So according to that, if I can see the model, then only I can say that okay, you can do this and that. But I think she can try she can try with the model with this infinite decimal concept and all this. If it will work, then okay. If it will not work, then think about the other method, like stochastic, fractional, or we can say fuzzy. So there are different. I only touch the fractional. There are a lot of different field modelings are there, like fuzzy modeling, fuzzy fractional modeling, stochastic modeling. Many things are there. So it's depending on your priority, what you are exactly going to do, and which one is more suitable for your problem.
Thank you, sir. Thank you very much, sir. Thank you for accepting our invitation in your busy schedule. And also we thank you, sir, for your motivating, valuable, and interesting speech, sir.
Thank you.
Finally, let me thank all the distinguished guests who have attended the meet to grade this occasion. Once again, I also thank the participants for their patient listening and cooperation.
Participants,
Participants who are going to present their papers in the conference are requested to join their respective links tomorrow by 10 a.m. sharp. We will be conducting a session of tomorrow's conference. If any queries, there will be given a mobile number in chat section. You can contact it. I repeat, participants who are going to present their papers in the conference are requested to join their respective links tomorrow by 9 a.m. sharp. We will be conducting 10 parallel sessions tomorrow. If you have any queries regarding this, you can contact the number which I will be giving chat section. Thank you all.
tomorrow at 9:30 a.m. all the participants should be joined with the respective presentation session in the WhatsApp group. I will share the schedule for the presentation. We have splitted all the 115 papers into the 10 parallel sessions. Please find the difference, since we have allotted different links for the 10. We have allotted 10 different parallel sessions. Please find your separate Google Meet link from the paper presentation schedule. And I request all the participants to join with the respective Google Meet link. Please find the link in the presentation schedule. Once again, I will share